Hi, this is Adam Griffin with the second video for this week, and we're going to be doing problem 4, which deals with conservation of angular momentum, as well as inertia. So problem 4 says that there's a solid turntable which consists of a uniform disk of radius r and mass m, and rotates on frictionless bearings about an axis through its center, and two blocks of mass lowercase m fall on the turntable opposite each other and come to rest at a radius of r/2. So find the final angular velocity, wf, in terms of the initial velocity, wi, and assume that the falling blocks initially have no velocity component in the transverse plane. So we have our angular momentum, which is represented with L, and this is our initial angular momentum, which is before the blocks hit it. So our angular momentum is equivalent to the inertia of our disk times the speed that it's rotating at. And this is what that is. This is angular velocity. So you multiply those together, that's what gives you your angular momentum. So the conservation of angular momentum says that L is unchanged. So before and after the blocks fall in it, it's still the same. So we have our final angular momentum is equivalent to our initial momentum, which is also our initial angular momentum, which is equivalent to I times the inertia of our disk times our initial angular velocity. So that means that after it is slowed down and we have our final momentum, that it is equivalent to the inertia of our disk times our final angular velocity plus our the inertia of our blocks times our final angular velocity. So to find both of these, we can take the equation for the inertia of a disk, which is 1/2 m times our radius squared. So if we plug that in, we can just turn that into a more simple equation. And then for the inertia of our blocks, it is the sum of the mass of an object times the radius from the pivot point squared. And then you do that for every mass in the system. So since we have two masses and they're both falling at a radius of r/2, that is our radius, so it's our lowercase m times r/2 squared. And we do that twice. So we now have m times r squared over 2 kilograms times meters squared for our inertia for the blocks. So we can plug these back in and we get that our final angular momentum is equivalent to these equations. So the one for the inertia of the disk times our final, and the one for the equation of our blocks times our final. And we can do some algebra here. We can simplify stuff. We get rid of the radius for all of them by dividing both by capital M r squared over 2. We can get rid of this term, and all we're left with is that our initial angular velocity is equivalent to our final plus our final times the mass of the block divided by the mass of our disk. So that is how you do problem number 4, and thank you.